Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Have you ever just stood outside on a perfectly clear, crisp night, like really far away from the city lights, and just looked up?
Oh, yeah. It's almost dizzying when you really do that.
Right. You just lean your head back, you let your eyes adjust, and suddenly you are staring into this massive ocean of stars.
It's a profound experience. It really makes you feel small.
It really does. I mean, you're looking at our own Milky Way galaxy, which is home to hundreds of billions of stars. And that is just one galaxy among, hundreds of billions more in the observable universe.
It's an incomprehensible scale, honestly.
Exactly.
Oh, yeah.
And when you let the sheer scale of that wash over you, a very natural, almost instinctive question bubbles up. Where is everybody?
Well, big one, yeah.
Right. In a universe so vast with so much potential for life to take root, why do you hear absolute silence? Like, why, when you point the most sensitive instruments we've ever engineered at the cosmos, are you just met with the deafening quiet of the void?
Well, it is literally the ultimate existential question in astrophysics, that silence it's heavy.
Yeah, it really is.
It's what physicists and astronomers have grappled with since the very dawn of radio astronomy. Because, you look at the numbers, the sheer statistical probability of other civilizations existing.
The Drake equation, right?
Exactly, the Drake equation. The math suggests the universe should be absolutely teeming with voices, yet the cosmic phone never rings.
Never rings.
Right, and this great silence is a phenomenon you just sort of internalize when you study the cosmos. You start to wonder, is humanity just a cosmic anomaly? Or, does intelligent life inevitably destroy itself before it can even speak?
Which is a terrifying thought.
Oh, completely terrifying. Or maybe the physical distances are simply too vast for any civilization to bother reaching out across the dark. You start treating that silence as an absolute fundamental truth of the universe.
And this is what we're getting into today. That narrative of a quiet, empty cosmos might actually be completely backward.
Yeah, it might be totally wrong.
The universe might actually be incredibly noisy. It could be saturated with greetings, with data, with the very signals you have been desperate to find.
Hiding in plain sight, essentially.
Exactly. The catch, and it is a massive galaxy-spanning physical catch here, is that the stars themselves, the very suns that give life to these potential alien civilizations, are acting as giant, chaotic scramblers.
Which completely changes the game.
Right. They are fundamentally distorting these alien messages before those signals even reach the empty void of interstellar space.
So the focus here is the incredibly violent physics of stellar weather. To really understand the great silence, you have to rethink the foundational assumptions of how an alien civilization would try to contact you.
You have to question everything we've been doing.
Exactly. You have to critically examine the biases built right into your own telescopes. Because for the better part of a century, the astronomical community might have just been looking for the entirely wrong type of signal.
Which is wild to think about.
It really is. The failure to hear them might not be because they aren't speaking. The failure lies in a fundamental misunderstanding of the altered, scrambled medium through which their voices are forced to travel before they ever reach Earth.
Okay, let's unpack this a bit. Because to understand why our search might be flawed, you really have to look at the historical baseline.
Right, how we've been doing it so far.
Exactly. For the entire history of the search for extraterrestrial intelligence, or SETI scientists have optimized their massive radio telescope arrays to look for one very specific, highly idealized thing.
Narrowband signals.
Yes. Extremely narrow spikes in radio frequencies. These narrowband signals are basically the holy grail. The entire infrastructure is just completely obsessed with finding these tiny, sharp slivers of electromagnetic radiation.
And, that obsession is rooted in a very real challenge, distinguishing the artificial from the natural.
Because the universe isn't actually quiet, right?
Oh, not at all. The universe is actually a tremendously loud place radiophonically. When you turn a massive dish, like the Green Bank telescope, to the sky, you don't hear silence. You hear a chaotic, roaring symphony of natural cosmic processes.
Like what kind of stuff?
Well, you pick up the lingering thermal hum of the Big Bang, the cosmic microwave background. You hear the violent, sweeping radiation from rapidly spinning dead stars, which are pulsars.
Okay, pulsars, right.
And you hear the colossal, galaxy-shredding engines of distant quasars. All of these natural astrophysical phenomena produce radio waves. But the energy they produce is smeared across a huge swath of the radio dial. It is wide, messy, chaotic noise.
It's kind of the equivalent of twisting the tuning knob on an old analog car radio and just hearing that loud, aggressive static across the entire band.
That is a perfect way to describe it. Natural physics is inherently messy. So the bedrock assumption of the search strategy for the last 60 years has been that an advanced extraterrestrial civilization would understand this fundamental reality of astrophysics.
Right, they'd know the universe is noisy.
Exactly. If they wanted you to hear them over the natural roar of the universe, they wouldn't broadcast a messy, wide signal that just blends in with the quasars. They would purposely broadcast a highly concentrated, ultra-narrow signal.
To stand out.
Yes. They would pack all their transmission energy into one tiny, incredibly specific frequency. Perhaps something mathematically universal, like the hydrogen line frequency of 1420 megahertz.
Because nothing in nature makes that specific sound.
Exactly. The logic dictates that an ultra-narrow signal cannot be created by a collapsing star or a black hole accretion disk. It violates the thermodynamics of natural cosmic emission. It can only be created by localized, purposeful technology.
It acts as a deliberate, undeniable techno-signature just screaming across the void.
Right, saying, we are here.
So imagine you're standing in the middle of a packed sports stadium during the final play of a championship game. Tens of thousands of people are screaming, stomping, cheering.
A totally deafening environment.
Exactly. That deafening roar of the crowd is the natural cosmic background noise. The pulsars, the quasars, the colliding galaxies. Now, if you are in the stands and you want your friend all the way on the other side of the stadium to hear you, you wouldn't just yell.
Right, a yell is just more crowd noise.
Exactly. A yell is messy. It just gets swallowed up by the crowd. To be heard, you would blow a highly pitched, ultra-sharp referee whistle.
Oh, that's a great analogy.
Thanks. That piercing, singular tone cuts through the chaotic noise precisely because it doesn't sound like a human voice or a stomping foot. That whistle is the narrow radio spike the arrays have been built to find.
And the sheer extent to which the search strategy, the software algorithms, and the telescope hardware have been heavily biased by this assumption is staggering. I mean, the massive, incredibly sophisticated arrays operating today are, at their core, ultimate whistle detectors.
Just waiting for that one sharp sound.
Right. The back-end computers run complex algorithms, fast Fourier transforms, to sift through petabytes of data, aggressively filtering out the roar of the stadium. They were literally mathematically trained to completely ignore the broad, messy noises, looking exclusively for that one sharp spike.
Which makes sense, logically.
It makes perfect logical sense based on a terrestrial understanding of radio engineering and signal-to-noise ratios.
Yep.
But a major variable was completely left out of the equation.
And what's that?
The physical environment in which the whistle is actually being blown.
Ah. So if the problem isn't the distance the signal travels across space, but the origin point itself, you really have to look at the immediate environment surrounding the transmitter.
Exactly.
Like what happens to that perfect piercing whistle if the environment it's blown in physically bends and warps the sound before it even leaves the stadium?
And this is where a groundbreaking study led by astronomer Dr. Vishal Gajjar at the SETI Institute comes in. It forces a direct confrontation with this exact scenario.
This is the paradigm shift we were talking about.
Yes. The study reveals a massive galaxy-sized blind spot in the traditional methodology. They identified a phenomenon called exo-IPM scattering, and they recognized it as a hidden gatekeeper of narrowband technosignatures.
Okay, so let's break down exo-IPM. Exo obviously refers to other star systems, exoplanets, that kind of thing. And IPM stands for the interplanetary medium.
Right.
But the word medium almost sounds too passive. Like the immediate volatile environment surrounding a star is anything but passive.
Oh, it's incredibly violent.
Right. You tend to think of stars as these quiet, stable, glowing orbs hanging peacefully in the dark vacuum of space. But up close, a star is a terrifyingly violent entity. It is basically a boiling ocean of plasma.
Just constant chaos.
Stars constantly blast out stellar winds, these hurricanes of highly energetic charged particles flying out into space. And they regularly suffer massive explosive events, coronal mass ejections, where billions of tons of magnetized plasma are violently hurled outward into the surrounding planetary system.
So, the space immediately surrounding a star isn't empty at all. It is packed with a turbulent, fluctuating, electrically charged plasma.
It's a storm.
Exactly. Now, insert your hypothetical alien civilization into this environment. They live on a planet orbiting an active star. They build a massive radio transmitter pointed at Earth and broadcast that perfect, ultra-narrow referee whistle.
The narrow spike?
Right. The signal leaves their transmitter, but before it can even reach the relatively quiet vacuum of interstellar space, it first has to punch through its own star's turbulent plasma storm. And the charged particles in that plasma interact intensely with electromagnetic waves.
Wait, okay, let me ask you something here. If an advanced civilization knows their star is blasting out all this charged plasma, wouldn't they just use a different communication method entirely?
Like what?
Like, why wouldn't they switch to optical SETI, firing high-powered lasers instead of radio waves, if they know the radio waves are going to get caught in the plasma storm?
That is a very fair question. And optical SETI is a valid alternative. Lasers definitely cut through plasma much more effectively than radio waves do.
So why wouldn't they just do that?
Well, because optical frequencies have their own severe astrophysical gatekeepers. While a laser ignores plasma, it gets heavily scattered and absorbed by interstellar dust clouds.
Ah, okay. The dust blocks the light.
Exactly. If the alien civilization is located on the other side of a dense nebula, an optical laser is essentially useless. Furthermore, radio remains the most energy-efficient way to broadcast an omnidirectional beacon.
Like a lighthouse.
Right. If you don't know exactly where the receiver is, sweeping the sky with a radio beam is vastly more economical than trying to target every single star in the galaxy with a laser. So the assumption that they would use radio holds really strong, which means the signal still has to contend with the plasma.
Okay, so the radio wave enters the plasma. It's kind of like shining a crisp, concentrated green laser pointer through a thick, swirling bank of heavy fog. Or actually like shining it through a heavily frosted, textured glass window.
That frosted glass analogy is perfect.
The fog, or the frosted glass, is the stellar plasma. What comes out the other side of the glass isn't a sharp pinpoint dot anymore. The structure of the beam is completely broken. The light scatters, bouncing off all the dense particles. What emerges is a wide, faint, diffused glow.
In astrophysics, we say the signal undergoes severe scattering and scintillation. The varying electron density in the stellar wind causes variations in the phase velocity of the radio wave.
Meaning the wave gets messed up.
Yeah, it leads to destructive interference. The immense, tightly packed energy of that narrow signal gets forcibly spread out across a much broader range of frequencies. The sharp, towering peak of energy weakens, it flattens, and it smears.
So what does that look like to the astronomers?
Well, when you look at these signals on a spectrograph, which is basically a visual map of frequencies over time, an undisturbed, narrow signal appears as a sharp, bright, continuous white line cutting vertically down the graph.
Very obvious.
Very obvious. But after it passes through the turbulent plasma of an active stellar wind, that sharp white tone gets smeared out. It shifts into a wider, fainter, much broader shape, often visualized as a hazy, indistinct smear on the data plot.
Wow! So the aliens blow the whistle perfectly, but by the time the electromagnetic waves actually make it out of their solar system's heliosphere, the whistle has been warped into a dull, broad roar.
Exactly.
The structure of the signal is stripped away, and it just sounds like the rest of the stadium noise.
And that's the tragedy of it. The signal still technically exists. The energy was transmitted, and it arrived at Earth. But its structural signature has been fundamentally transformed from an obvious technosignature into something that perfectly mimics natural, messy, cosmic background noise.
The whistle becomes a roar.
The whistle becomes a roar. And remember those back-end computers on the telescope arrays? They are programmed to aggressively filter out the roar.
They just delete it.
They toss it out as junk data. If a signal gets broadened by its own star's environment, it slips completely below the contection thresholds. The algorithms only want the sharp lines. They completely ignore the hazy smears.
That is so frustrating.
It really is. The astronomical community has likely been systematically throwing out the very signals they are trying to find, all because the alien star scrambled them before they even reached the interstellar highway.
Okay, but that raises a critical methodological question here.
Sure.
These are entirely theoretical alien signals interacting with theoretical alien stellar plasma. Since you can't exactly travel to a distant star to run a field test, how do they actually prove the specific physics of this scattering?
Right. How do you test it?
Yeah. How do you calculate the exact mathematical relationship between turbulent plasma density and the smearing of a narrowband radio signal without an actual alien transmission to measure?
Well, the researchers didn't just rely on abstract mathematics or pure computer simulations. They knew they required concrete physical proof of how plasma scrambles narrow signals in the real universe. And they realized they actually had access to a perfect, massive, localized laboratory right here, our own solar system.
Oh, of course.
Yeah. You have an entire fleet of robotic spacecraft operating right now within our heliosphere. The Voyager probes out past the termination shock, the New Horizons spacecraft, the Mars Reconnaissance Orbiter, the Parker Solar Probe.
They're essentially human-made extraterrestrial transmitters.
Exactly. They communicate with Earth by beaming back incredibly narrow, highly concentrated radio telemetry. They are blowing the exact kind of referee whistle SETI is looking for, so that the deep space network antennas in California, Spain, and Australia can actually hear them over the background radiation of the sun.
That is so smart. So the researchers just repurposed our own deep space probes as stand-ins for the alien transmitters.
Brilliant, right. By observing the narrowband radio transmissions beamed back to Earth from our own solar system probes, the scientists could monitor exactly what happened to the physical structure of those signals when they pass through different regions of our own sun's stellar winds.
How does that work geometrically?
The technique is related to radio occultation. They could measure the crispness of the signal when the probe was far away from the sun, in relatively quiet space, and then compare it to the heavily degraded signal received when the orbital geometry caused the line of sight to pass dangerously close to the sun's turbulent corona.
Or like right through the path of a solar flare.
Exactly. They gathered mountains of localized measurements, literally watching the laser pointer hit the fog in real time. They knew the exact initial shape of the probe's transmission, and they measured the exact distorted shape that arrived at the deep space network.
Okay, so they built a baseline.
Right. Once they established that solid, proven baseline of how space weather affects signals locally, they could scale the physics. They could take those concrete measurements and apply them mathematically to various stellar environments across the galaxy.
That makes total sense.
The calculations allowed them to say, if our sun, which is a relatively calm G-type main sequence star, scatters a signal by a specific metric, what is the exact broadening effect if the signal originated around a star with a stellar wind 10 or 100 times more dense?
Here's where it gets really interesting, though. If NASA engineers and heliophysicists have known about this signal distortion for decades, because, they literally have to account for solar plasma smearing the telemetry from Mars rovers, why did it take the SETI community this long to realize it would happen to alien signals, too?
That is the million-dollar question.
Right. Surely the astronomers listening for aliens knew about the interstellar medium. Why is this a totally new paradigm?
Well, the SETI community was highly aware of the interstellar medium, that incredibly thin, sparse dust and ionized gas that exists in the light years between the stars.
The deep ocean of space.
Right. The interstellar medium does cause a minor amount of signal scattering. Radio astronomers build complex algorithms into their systems, things like de-dispersion filters, to account for the slow degradation of a signal as it travels across thousands of light years of the interstellar ocean. They meticulously model the distortion of the long journey.
But they were so focused on the deep ocean, they completely forgot to look at the shoreline.
That is exactly what happened. They completely overlooked the extreme, catastrophic distortion happening right at the origin point. The assumption was just always that the signal entered the interstellar ocean perfectly intact.
Which is a huge oversight.
It is, but the delay in recognizing this exo-IPM gatekeeper is actually a classic example of the siloing of scientific disciplines.
People not talking to each other.
Exactly. The engineers operating the Deep Space Network and the heliophysicists studying the sun's local space weather belong to one distinct academic community. Their focus is entirely on maintaining probe communication and protecting terrestrial grids from solar flares.
And SETI is over in a different building.
Right. The radio astronomers and SETI researchers belong to a completely different community, with their focus locked on the vast expanses of deep space. It took a massive interdisciplinary synthesis of local heliophysics and distant SETI targeting algorithms to create a unified framework. Someone finally had to step back and realize, hey, the aliens have to transmit through a sun, too.
Wow. And once that interdisciplinary framework was built, bridging local solar physics with galactic SETI searches, the numbers they ran on the rest of the galaxy completely broke the existing map.
Completely broke it.
Because when you look at the distribution of stars in the Milky Way, you realize our calm yellow sun is actually an extreme minority.
A huge minority. If you look at the true rulers of the Milky Way, you are looking at M-dwarf stars, which are also known as red dwarfs.
M-dwarfs, right.
They're smaller than our sun, much cooler, and they burn a dim reddish color. But what they lack in mass, they absolutely make up for in sheer overwhelming numbers. Roughly 75% of all stars in the Milky Way are M-dwarfs.
75%.
3 out of every 4 stars you could ever point a radio telescope at are these small red suns. Mathematically speaking, if exoplanets harboring life are out there, it is highly statistically probable that they are orbiting an M-dwarf simply due to the ubiquitous nature of these stars.
And this is where the physics of the exo-IPM scattering really collide with the reality of the galaxy. Because if M-dwarfs are smaller and cooler, you'd intuitively think their stellar weather would be quieter, right? Like a smaller fire is less violent.
You would think so, but M-dwarfs are notoriously violent.
Way more violent than our sun.
Oh, exponentially more. Their violence is a product of their internal structure. Because they have a lower mass, usually between 0.08 and 0.6 solar masses, many M-dwarfs lack what's called a radiative zone. They are fully convective.
What does fully convective mean for the star?
It means the boiling of plasma from the core all the way up to the surface is incredibly chaotic and continuous. It's just churning constantly. This deep convection creates tangled, massively powerful internal dynamos, which generate extreme magnetic fields.
And when those fields snap.
Exactly. When those magnetic field lines snap and reconnect on the star's surface, they unleash titanic stellar flares. An M-dwarf might be a fraction of the size of our sun, but it can unleash space weather superflares and continuous dense plasma storms that completely dwarf anything our sun produces. Their immediate environments are just roiling cauldrons of dense, turbulent plasma.
Okay. And because M-dwarfs are so cool, their habitable zone, the orbital distance where liquid water can exist on a planet's surface, is incredibly close to the star.
Very close. They have to huddle up for warmth.
Right. So a planet like Proxima Centauri b, or the worlds in the TRAPPIST-1 system, they are tucked right up against their host star. So a hypothetical alien transmitter isn't just in the solar system, it's practically inside the thickest, most violent part of the plasma storm.
You see the exact nature of the dilemma now.
It's a nightmare for communication.
Total nightmare. The study revealed that M-dwarf stars are exponentially more likely to severely broaden narrowband radio signals before those signals can ever escape the planetary system. The plasma fog around an M-dwarf is so thick and the transmitter so deep inside it that a narrow radio spike basically doesn't stand a chance of surviving intact.
So what does this all mean? If 3 out of every 4 stars in our entire galaxy are M-dwarfs, and M-dwarfs inherently scramble narrow signals into a wide blur, we have basically been applying a search filter that intentionally, actively ignores 75% of the galaxy.
That's the painful truth.
You are staring at an ocean full of fish, using a net mathematically designed to let 75% of them swim right through.
It perfectly addresses the Great Silence. It provides a highly plausible, purely physical mechanism for the Fermi paradox in the realm of radio technosignatures. The alien civilizations might be there. They might be transmitting continuously.
We just can't hear them.
Right. Those signals could literally be washing over Earth's radio telescopes at this exact moment. You aren't failing to detect them because space is empty. You are failing to detect them because they have slipped below the highly biased, narrow detection thresholds built into your computers.
Because they look like noise.
They don't look like the sharp, unnatural spikes the algorithms want. They look like the messy, chaotic noise of the universe. The environment acts as an insurmountable physical gatekeeper to the communication medium humanity deemed most logical. The plasma simply doesn't care about terrestrial search algorithms.
It's effectively a galactic mute button.
A galactic mute button,
exactly. Now, talk about it. An advanced civilization on an M-dwarf planet spends immense planetary resources building a massive transmitter array. They calculate the exact mathematical frequency to broadcast a perfect, crisp signal. They fire it into the dark. and their own sun immediately shreds it into cosmic static before it even crosses the heliopause.
Tragic, really.
And then on Earth, our algorithms look at that static, categorize it as quasar noise, and just delete the file.
But, identifying this colossal galactic blind spot isn't actually a defeat. It is a massive victory for the field.
Because now we know.
Exactly. Discovering that a search methodology is physically flawed means you can finally begin searching the right way. It is the necessary destruction of an old paradigm so a more accurate one can be constructed. Future searches have to evolve, and this study provides the rigorous physical roadmap for that evolution.
Right. As Grace C. Brown, who is a research assistant at the SETI Institute, noted, searches must be designed and matched to what actually arrives at Earth, not just what you imagine might be transmitted from the source.
That is the core takeaway. You have to stop designing your tools based on the idealized, pristine origin of the message and start designing them based on the battered, bruised, weather-beaten reality of the message that actually washes up on the telescope dishes.
So this means target selection and search strategies are going to fundamentally shift.
Oh, completely.
Ah.
For decades, if a telescope pointed at an M-dwarf and the back end only registered broad, noisy signals, the system would immediately discard the data and move to the next star. Now, those broad signals have to be preserved. They have to be analyzed with entirely new mathematical approaches.
We need new tools.
You have to develop machine learning algorithms that don't just look for isolated spikes, but can actually analyze wide, blurry bands of radio energy to detect hidden underlying artificial structures buried within the smear.
You basically have to build better fog-piercing goggles. But I'd imagine you can't just flip a switch on a massive radio telescope array and tell it to suddenly care about broad signals.
Oh, it's that easy.
You have to write entirely new code, build new wideband receivers, and process astronomically larger data sets, because if you stop filtering out the noise, you suddenly have an overwhelming mountain of data to sift through. The computational power required to run broadband analysis on 75% of the stars in the sky must be absolutely staggering.
It is a monumental engineering and computational challenge. And proposing an entirely new, unproven methodology that requires massive computational upgrades is risky. It is notoriously difficult to secure traditional academic funding to search for something that the rest of the community previously dismissed as junk noise.
Because traditional grant committees usually require a high probability of success, right, or a guaranteed return on investment. They want to fund the safe bets, not the structural overhauls.
Right, and that is why initiatives like the SETI Institute's STRIDE program are absolutely vital here.
STRIDE, that stands for Support Technology, Research, Innovation, Development, and Education.
Exactly. It is specifically designed and funded to support this exact kind of high-risk, high-impact research. In this case, the research was significantly championed by the Franklin Antonio Bequest. It provides the financial runway for scientists to ask the brave questions, to challenge 50 years of established dogma, and to secure the computational resources necessary to analyze the messy, widened signals that the old algorithms just threw away.
It really takes a specific kind of philanthropic vision to fund the rogue ideas that force the entire community to admit their current infrastructure might be looking in the wrong direction.
It really does. It's an investment in intellectual honesty. It offers a profound lesson in the philosophy of science, really. True critical thinking means rigorously questioning your own assumptions, especially when your assumptions are your greatest vulnerability.
Because we assumed so much.
We did. The search for extraterrestrial intelligence assumed aliens would engineer signals like humans do. It assumed their stellar environment was as relatively calm as our own solar system. It assumed terrestrial definitions of noise and signal were universal truths.
And the universe humbled us.
The universe absolutely humbled those assumptions. It reminded the astronomical community that the cosmos is wilder, messier, and far more complex than a pristine radiograph. But, in breaking those assumptions, it provides a massive renewed sense of hope.
Because they might actually be out there.
Exactly. The great silence might simply be an inability to understand the cosmic dialect of a violently churning plasma sea.
It fundamentally changes how you look at the night sky. You move from the heavy feeling of an empty, silent galaxy to the realization that the void might be buzzing with distorted, widened signals that are washing over the planet every single day. You just need to build the right tools to read the fog.
It is a complete recalibration of our cosmic senses. It requires patience, immense computational innovation, and the humility to let the physics of the universe dictate the terms of engagement.
So as we wrap this up, I want to leave you with one final concept to ponder, building entirely on the physics of this exo-IPM gatekeeper. We spend so much time conceptualizing the alien transmitters and how hard it is to hear their signals through the violent weather of their M-dwarfs. But flip the mirror, look at our own sun. Yes, it's relatively stable compared to a red dwarf, but it is still an active, burning ball of plasma. It has solar flares, coronal mass ejections, and a constant, dense stellar wind. And for the last 100 years, humanity has been leaking its existence out into the void.
All of our TV and radio.
Exactly. The early radio broadcasts, the powerful sweeps of military radar, the deliberate attempts to beam messages toward distant star clusters like the Arecibo message. When those eager, narrow terrestrial radio broadcasts bleed out past Jupiter, past Pluto, and smash into the turbulent plasma boundary of our own heliosphere, what happens to them?
They get scattered.
What does humanity sound like to the rest of the galaxy? Are there alien astronomers sitting on a distant exoplanet staring at their own readouts, wondering why the universe is so quiet?
Probably.
Are they out there right now relying on their own flawed algorithms, listening for a sharp, perfect whistle, completely unaware that our own sun has violently scrambled humanity's desperate hello into an unrecognizable, hazy whisper in the cosmic wind? It's a haunting thought. The gatekeeper works both ways. The very star that gives humanity life might be the shield that prevents the rest of the universe from ever hearing it speak.
Keep looking up, keep questioning the silence, and keep searching the static.